In this video, we will discuss about the air filters that are present in maybe automotive industry or aircraft or any air conditioning. So wherever the air filters are present, so how to operate those air filters in, or how to simulate those air filters in CFD, and how to verify what is the number of particles that are trapped inside that air filter, as well as what is the life of the air filter. So as the number of particles are being trapped, the mass of the air filter would increase, and it also obscures the new particles, it obscures the airflow that can be transferred through this porous media. And so that as a more and more particles deposit, it is not a viable solution to use that air filter anymore because of the huge pressure drops. So we would remove that air filter, we clean, and we need to replace, or we need to create replace with a new filter altogether, right? So now, as you can see on the screen, so these are the air particles which is having the carbon deposits, or maybe particulate matter for that course, of different diameters. Maybe the diameters can vary from for in our example case, we will take 1 e power minus 7 to 1 e power minus 5. So this is the range what we try to simulate. So these are the range of the particle dias that are coming onto an air filter. And now, so we'll keep a criteria saying that anything more than 5 e power minus 5. So this is the dia. The particle size is more than 5 e power minus 5. It will be trapped because the diameter of this porous media would be 5 e power minus 5. So anything more than this, the particle size will be trapped. Anything less than this, so it will allow. So along with the air, those particles which are less than 5 e power minus 5 dia will flow through this filter, right? So this is the example what we are taking, and it's not that 5 e power minus 5. If you have a very fine filter, it can go up to 1 e power minus 7. So any particle dia more than 1 e power minus 7 will be trapped, right? So for our case, we are taking 5 e power minus 5, or else maybe we can reduce it to bit. So we can take 1 e power minus 6 as our dia limit. So 1 e power minus 6, anything more than 1 e power minus 6 will be trapped here. Less than 1 e power minus 6 will be going through this filter. Okay. Now this is a sample domain what we have considered. So this part is symmetry, and this front and this back are symmetry, top and bottom. So all these four faces are symmetry, and from here the air is entering. So we will take certain velocity with which air is entering, and this is the air exit. So in our procedure, what exactly we do is, so first we perform the steady state analysis. So we perform steady state analysis to verify how the pressure is dropping across this porous media. So this is all porous media. Okay, so this is a porous media. Sorry, this we'll leave it. This is not a porous media. Only these things we'll just. So this will define as a porous media up to here, and here this is the interface from which particles are injected. Okay, so now any particle coming onto this, either it should go through this point or it should stick at this point. So this is the particle trap what we say. So anything less than 1 e power minus 7, it will flow across. Anything less than or greater than 1 e power minus 7, it will trap here, right? As the time progresses, more and more number of particles will trap, and it will not allow the air to pass through, right? So this is a complicated simulation. So we will split into two parts. Part 1, so we will see the UDF and all the things for the particle trapping, right, when the diameter is greater than 1 e power minus 6. In the part 2, so we will also include this particle trap mass, how it affects this porosity. I mean, so initially this is a plain domain, but as more and more particles gets deposited, so what happens is, this is not a free air domain. It will be a porous domain with a more number of particles, right? And it will create some resistance to airflow. So that would be simulated in the part 2. So this will take it as a part 1, where we will try to check the UDF, how it exactly bothers about this trapping of the particles due to this change, as well as So there is a porous jump that would be present here. So you can see this is a thin sheet, maybe like 1 e power minus 3 mm we will take, sorry, 1 e power minus 3 meters, 1 mm thickness porous material. So when the air flows across this, so it will has a viscous resistance as well as inertial resistance, we know that, right? So we'll take inertial resistance as 8000 meter inverse and viscous resistance as 10 e power 8 meter square, the values. So these we will be integrating onto this porous jump condition. So air that is striking here, so we'll have this pressure drop due to this porous jump condition. Okay, and the particles which are more than 1 e power minus 6 dia will be trapped here. We'll check how can we do this in the simulation with the help of an UDF. So maybe first we'll go to it's a steady state. As we stated, we'll first run the steady state, and for this we'll have the air, and we'll so this is the porous interface. I'll show you, right? And this is a particles which it will trap. Okay, so now what we'll do for this interior, we'll change this to porous jump condition, right? And porous media thickness, as we discussed, we'll give it as this one, and this is a 8000. Okay, so this is a porous jump condition what we have given, and the inlet air velocity we will be giving maybe 0.01 meters per second. This is the air velocity. Then we'll run this steady state simulation. We'll check how it behaves. So we have not activated any discrete phase modeling. So that once the steady state is performed, then we can activate the discrete phase without running the flow simulations anymore. So that would save the time and the computational efforts also. It's just a demonstration purpose. I'll stop all, and we are not bothering about the convergence and everything. And we'll check how the counters look like. It's not fully built. I think we need to run some more iterations. So I'll run some more iterations and I'll get back. We'll go with the pull. I think we can go with a simple scheme. We'll just check. It's very less time consuming. I'll get back once the solution is. So now the solution is converged. We'll check how the counters look like. Yeah, it is pretty much decent now. So you can see there is a pressure jump across this. Here there is more pressure, here there is less pressure, because the more velocity will get staggered here to the static pressure value. And similarly you can see the velocities, how it exactly looks like, right? And maybe we can increase the velocity a bit more value. I'll just check. Now this definition, let it run and converge. So now it is converged with 1 e power 0.1 meters per second. We'll just check how the pressure looks like. So it will be more in number. So you can see 0.012. Significant impact is there here. Then now we'll start injecting the particles now. So we need to turn on the DPM. Interaction with continuous phase. So we'll try to say that for every iteration you need to update and unsteady particle tracking. So the particle time step is 0.001 with the number of time steps as 1. Okay. Now I will create an injection, a new injection. I create an anthracite which is near to carbon density and things. So I'll use that as my material. So which is approximately near to carbon only. So then I'll try to inject from this porous interface. Okay, you can just refer the porous interface. Then now here the point, we cannot take a single particle size, so we need to consider different set of particle dias. So now I'll say that inject using phase normal direction. The velocity is automatically taken from the velocity that we get from the fluid, so we need not bother there. and the time step maybe I'll select as 500 seconds right now. The total flow rate I'll set this as 1 e power minus 10. Now here, so we have selected 1 e power minus 7 as minimum diameter and 1 e power minus 5 as maximum dia, right? And mean dia right now we can take it as 1 e power minus 6, right? The spread parameter and the number of diameters. This is important point how we will set this, what exactly this means. So I'll just open a Word document. This is the Rosin Rammler distribution. Maybe I'll just, for example, I have taken these notes to explain it to you. When we have given these bins and the spread diameter, so in each bin, it's like, so there would be 3 bins. For example, I'm stating it. In these 3 bins, we have given the maximum dia as 1 e power minus 5 and 1 e power minus 7. So this is 1 e power minus 5, and these 2 we don't know, and 1 e power minus 7 we do know. So now this 1 e power minus 7 and 1 e power minus 5, with respect to these 2 would be interpolated. Those values we'll get. Now maybe those values we'll assume somewhere around 1 e power minus 6 and this maybe 3.1 e power minus 7. The example like I'm saying. So now 1.1 e power minus 5 and 1 e power minus 6. So what is the fraction of the particles that are coming from this point? We are injecting from this interface, right? Maybe if you inject 5 particles, out of 5 particles, how many fall under this bin, how many fall under this bin, how many fall under this bin, right? Maybe 3 particles here, 1 1, or 2 2 2 1. So how exactly that is getting distributed? That is done using Rosin distribution. So that distribution I'll show it to you. So here you can see the distribution, right? 1 second. So this is the distribution. 1 minus e power minus d by d mean, right? And this n is called d mean, and this n is called spread. Spread parameter we have mentioned 3.5. So now exactly I have stated 3 bins, 1 e power minus 7 to 3.16 e power minus 7, and this is another bin range, and this is another bin range, right? So at each specific dia, so we will be getting the fractions. For 1 e power minus 7, what is the probability? For f 3.16 into e power minus 7, so what is the probability? Now fraction in bin would be difference of this value minus this value, that gives the fraction. This is the fraction in first bin, and this similarly for the second bin, and similarly for the third bin. How many you will give? 4 bins, 5 bins. So in this way, each bin with respect to the mean dia and its own dia, it will try to calculate what is the average number of particles that can be persisted in the single bin, right? So depending on this only, it will try to calculate. So this is for Rosin Rammler. Similarly, you can use the Rosin Rammler logarithmic also. I have given both for the explanation, logarithmic spacing, and this is the normal one. You can see here, right? So now, even though you mentioned 1 e power minus 7 and 1 e power minus 5 as your minimum and maximum, the particles, average particle size in each bin will not be the same value. You can see. So this would be the average of these two, and 1.7 into e power minus 7, right? So now from each bin with this fraction, the particle dia that would be coming out is this, not either 1 e power minus 7 or not either 3.16 e power minus 7. So even though in Fluent you mention this value upper limit and lower limit, the value it takes is the average, right? So these are the 4 diameters with which the particles come out of the injection point. As you see here, from this injection point, so these are the 4 particle dias. If you give 4 bins, now I have mentioned 10 bins, so accordingly 10 diameters will come, which is not a integer at all. So it would be a real number, okay? And what is that amount of mass that it each takes? So for example, 1 e power minus 10 mass kg per second we have given, out of which this would be 0.00245 into 1 e power minus 10. and this is 0.00775 into 1 e power minus 10. We have mentioned here, right? 1 e power minus 10. You can see here 1 e power minus 10 as our flow rate. So out of which each bin has the definite mass fraction multiplied by this one, right? So we will be taking spread parameter as 3.5, number of diameter as 10. Click OK. Close. Now we will go through the actual UDF. I will just show you. This is the UDF. So for each iteration, we'll call this function define adjust, right? In this define adjust, the particle injection porous jump ID is 7, right? Sorry, 1 second. So we should consider the cell zone and the ID is 4. So the inside air what is present. So what I am defining is inside air means, sorry, inside air is this domain. So I will just highlight it for you. This is the inside air and this is the outside air. So inside air ID is 4, right? So with that inside air ID, I am just using this UDF to loop over all the cells, right? And I am trying to increase that value when I am looping it by NOP. I mean that is an integer value. I am just increasing it and I am trying to find this, right? So when I am trying to do this, if the number of particles trapped on the interface would increase with respect to this. Now what is this value? How is C underscore UDMA C comma T comma 1 is initially patched with 0, but the value need to increase, right? So we are initially patching this user defined memory with 0 value. So as the time progresses, this counter should increase and it increases the NOP. NOP is an integer. So this is somewhere linked with this boundary condition, right? You can see here the velocity of the particle which is coming and hitting the wall, if it is less than the critical velocity, then we are increasing the counter. So the C underscore UDMI F underscore C naught F of F comma T naught comma 1 is nothing but the same function, okay, and its count is been increased by 1. So what is critical velocity? So critical velocity, we have this formula. So this helps in understanding, so what is the velocity with which a particle will try to fail to revert back on hitting the wall. So maybe I'll just show this way. So a particle is coming, is going and it is hitting, right? So when it hits, so there is a critical velocity. If that hitting is not maintaining this critical velocity, it will go and trap, okay? So it should maintain this critical velocity in order to come back. If it is less than this critical velocity, it will trap. This is the criteria what we are taking. And if the diameter should also be less than 1 e power, sorry, should be greater than 1 e power minus 6, then only it will go and hit, or else it will go pass through this porous jump interior condition, right? So if it is greater than 1 e power minus 6 only, we'll go into the loop and we'll check whether it is crossing this critical velocity or not. So there will be two if loops. If you can check, first if loop is, so we'll mention this 6. So diameter should be greater than 1 e power minus 6, and it will solve everything to find out the velocity of the particle. This is the velocity of the particle. You can see. So these are the velocities of the particles. So velocity of the particles have three components: x, y, and z. Right. So this is the procedure how you try to calculate the velocity of the particle when it is hitting. It's not that it is ideal when it after it hits. So what is the velocity? This is the velocity after it hits based on the normal and tangential coefficients, right? Now once it hits and it comes back, this is the velocity with which it comes back. And if that velocity, you can see that velocity Vn, if it is greater than Vcr, it's okay, right? So Vn we have defined in this way, which is the velocity into the normal direction, right? That is a Vn, and if that velocity is greater than VCR only, it will bounce back. If it is less than VCR, we will say that return path end. I mean the particle now it should not return back, it should trap there. So the particle would be trapped, and thus counter would also be increased. What is this f underscore c naught comma f comma t is? You can see these are the cells which are just adjacent to this interior. So that cell is being defined by f underscore c naught comma f comma t. This f is this phase and t is the phase thread, right? What is this phase? We know that phase is nothing but 7, particle injection porous jump id with 7. So that is the reason why we have mentioned that boundary, and it will take this thread and that phase. Phase is nothing but the 7 id. Okay, so it will verify for that. And with respect to the f underscore c naught comma f comma t, it gives the cells which are adjacent to that phase. Into that variable I am saving this +1. So if it is less than VCR, the particle count increases, and I am also storing the mass of the particle. So mass of the particle is nothing but the volume of the particle, which is pi by 6 into d cube. D is nothing but macro is given with the help of this tp underscore diam of tp. So this gives the particle diameter, right? And we should add power of, it is 1 second, comma 3. Okay, this gives the pi by 6 d cube into density 2097. So this gives the single particle which is trapped onto the layer mass, right? And it returns the path in. Now if Vn is greater than Vr, so we cannot now stop that. Now we need to get back the velocities which are created, and that would be injected into the tp underscore velocity 0, right? So this velocity 0 is nothing but more the retrieving velocity. So once it hits, how it comes back and how it travels and all those things. So that is the new velocities that need to be assigned to the particle after the it is hitting, right? This is a UDF, and we'll just check how can we integrate that. So this is the part. Now if the diameter is less than that 1 e power minus 6, it need to go through this interior, right? So when it is going through the interior, now we need to intentionally keep these particles from these phases to this phase, right, without any obstruction. That is carried out by this part. So it will store that f underscore c1 comma f comma t comma t1, and it will make the particles to jump to the neighboring cell, and it helps the return the path active. It means the particles will be in active state. But in this case, as you see, we are using the f underscore c naught, means the particles which are hitting and having more than critical velocity, it will retain in this cell, not it will pass through the cell. So it will retain in the same cell, and with the different now velocities and magnitudes, it will travel, it will tracks, what I mean to say. And that is also part return path active. But if it is less than VCR and the diameter is greater than 1 e power minus 6, then definitely it will have a return path in. The particle will be trapped, and the number of particle traps should be taken care by this. The mass of the particle trap will be taken care by this. Okay, so now we can also print this value. Maybe I'll print mass is equals to this is 2 mass initially is equals to 0. Okay, so it will print, and if you want we can print the mass, or else directly we can see this value in the Fluent. Okay, now I'll try to save it and compare it in the Fluent. So pi it is not able to identify. I'll just do one thing. It is 3.14. I'll directly mention the value. We'll remove it. I'll hook this and I'm hooking it. So in the defined boundary porous gem, we'll use this user defined by filter, and also we'll function that define edges for every iteration to verify how the particles are getting trapped. I'll remove this because we already have this solved equation. We'll only track the interface, sorry, particles. In this I'll try to mention randomized starting points. Maybe I'll keep only 4 number of streams instead of having all. We can create a few particle tracks to see how it exactly do the things. Save display. Now there will be no particle tracks. What we'll do, so we'll create a scene to identify how the particle tracks are. Save display. We'll also create a counter doing all these things excluding this point. Close this scene. We create this counter. Will increases transparency. We'll check now. So now this is how it looks like right now. Don't worry, I'll attach the files in the description. You can have these things. So now we'll run things. Okay. Sorry, I need to forward to remove this. So I need to remove this again. We need now we'll create an animation here so that you can visualize the particles motion. For every 2 time steps, 2 iterations, the scene use active. Okay, we'll check. This is so. I think it is very we'll zoom the image. We'll check once. The save display. Yeah, this is okay. Initially, we'll just save. Check the preview also of this. So we'll zoom in. Okay. These are the particles. Okay. Active. Now, are we able to see any particle trapping? We'll check. We'll start the things. We'll get back after some time. So now you can see there are a number of particles trapped on the interface is equals to 4 as it mentioned in the UDF. So whenever at the interior of that porous gem, if it maintains this criteria, Vn is less than Vcr, so velocity is less than the Vcr, so now the particles are getting trapped. That will be only increased when this is met the criteria, and that criteria I'm trying to print the message. So the number of particles trapped are present here, that is 4, and we can also verify that number count in the reports. Volume integrals, sum, user defined memory, and 1. Select this and compute. You can see 5 are the number of particles. So here on the interface 4, in the next iteration you get 5, so it is 5 the number tracked, and you can also get the mass that is being deposited due to this trapping. It's very low, of course, because the particle diameter is very low. Okay. So in the next video we will discuss about how these particles trapped would increase the resistance and create a porosity in the inside air domain. Inside this domain, how this creates a porous domain and how it tries to reduce the air flow due to the particles that are being trapped. Thank you.